Imagine a vast, shifting expanse of Arctic sea ice, billions of tons of frozen water moving slowly, relentlessly, across the polar ocean. For centuries, this motion has shaped the climate, influenced ecosystems, and dictated the safety of ships, scientists, and indigenous communities alike. But how do we measure it? For decades, researchers have relied on sparse buoys, floating sensors drifting with the ice, tracking their positions via GPS. These provide valuable data, but only at a few points. The gaps between them. That's where the real story of ice motion lies. Subtle deformations, fractures, leads, and the complex dance of floes colliding and breaking apart. Now a breakthrough is emerging, using deep learning to estimate sea ice drift not from a handful of buoys, but from every pixel in a satellite image. This is the story of how deep learning optical flow, a computer vision technique once confined to movies, robotics, and self-driving cars, is now being used to map sea ice motion across the Arctic with unprecedented detail. Let's dive into the science. The challenge, seeing motion in the ice. Sea ice drift is critical, not just for climate models, but for navigation, search and rescue, and predicting how the Arctic will change as global temperatures rise. Traditional methods like cross-correlation or feature tracking work well in some cases, but fail where ice is thin, featureless, or rapidly deforming. They struggle at flow boundaries, in leads, or when ice is breaking apart. And because they're sparse, they miss the fine-scale dynamics that shape the ice's behavior. Enter optical flow, a method that estimates motion at the pixel level. Given 2 consecutive images, it assigns a vector to every pixel, showing not just if something moved, but how far and in which direction. In computer vision, this has been revolutionized by deep learning. Models like RAFT, DPFlow, and SEA-RAFT don't just follow mathematical rules. They learn from millions of examples, adapting to complex textures, lighting changes, and large displacements. But here's the catch. These models were trained on natural images, RGB photos of streets, forests, and cities. The Arctic. It's not a street. It's a radar image, SAR data, full of speckle noise, low contrast, and textures that don't exist in the real world. So can these models work in the Arctic? That's exactly what this study set out to test. Researchers from the University of Delaware and Drexel University conducted the first large-scale benchmark of 48 pre-trained deep learning optical flow models applied to RADARSAT-2 ScanSAR imagery, a high-resolution, wide-area radar dataset collected during the 2021 Sea Ice Dynamics experiment in the Beaufort Sea. They used 54 satellite images taken over 2 months, capturing everything from compact ice to open leads and fracture zones. Each image was resampled to 50 meters per pixel and cropped around the position of 43 GNSS-tracked buoys, including high-precision SAT-ICE buoys recording positions every 5 minutes. To make the analysis fair and consistent, they applied the 48 models without fine-tuning, using only their pre-trained weights. Why? Because the ground truth is too sparse. Only 1,880 buoy displacement observations across the entire dataset. Training a model on that would risk overfitting, learning noise instead of real motion patterns. Instead, they evaluated performance using 2 standard metrics. Endpoint error, EPE, the average Euclidean distance between predicted and actual motion vectors. Lower is better. Flow outlier rate, FLL, the percentage of pixels with errors exceeding 3 pixels or 5% of the local displacement. This measures robustness to gross errors. And the results? Here's the big surprise. 75% of the models achieved an EPE of just 6 to 8 pixels, about 300 to 400 meters. That might sound like a lot in a computer vision context, where subpixel accuracy is the gold standard. But in the Arctic, where ice drifts tens of kilometers over days, a 400-meter error is negligible. For example, one model, DIP, Scintille, achieved an EPE of just 6.29 pixels, less than 320 meters, while keeping a relatively low FLL of 42.5%. Another, DPFlow chairs, matched that precision with even better robustness. But here's the nuance. FLL scores were high, around 43%, because the metric is extremely strict. It penalizes any pixel with an error above 3 pixels, even if the overall motion field is accurate. Yet in the Arctic, such errors are often not catastrophic. A single misclassified pixel in a large, coherent drift pattern doesn't break the big picture. What matters is whether the model captures regional drift pathways, the dominant flow directions across tens of kilometers. And it does. Take a look at a representative image pair. The 3 top-performing models, DIP, RPKNet, and SEA-RAFT, each produce a dense motion field. Using the standard color wheel, where hue indicates direction and saturation indicates speed, we see clear drift blocks, regions of coherent motion. The ice near the center moves slowly, while motion intensifies toward the edges, exactly as expected in a Lagrangian frame of reference, where the image patch moves with a buoy. All 3 models agree on the direction of motion, capturing consistent regional drift. But differences emerge in magnitude. RPKNet systematically underestimates speed, especially where motion blocks converge. It also introduces spurious high gradients along image borders, artifacts that don't correspond to real ice dynamics. DIP and SEA-RAFT, in contrast, produce smoother, more physically plausible fields, better preserving large-scale structure. This matters for real-world use. For navigation or early warning systems, A slightly conservative, stable estimate is often more reliable than a fine-grained but noisy one. This isn't just about better accuracy. It's about transforming how we understand sea ice motion. Traditional methods give us motion at discrete points. Optical flow gives us motion at every pixel, a continuous spatially resolved drift field. That means better climate models that can simulate ice dynamics at finer scales, improved navigation tools that predict ice movement across entire routes, faster response to emergencies, like oil spills or search and rescue missions, by tracking how ice will move in the next hours or days. And the best part? These models work out of the box. No need to retrain on Arctic data. The generalization power of deep learning, developed on natural scenes, translates surprisingly well to SAR imagery. Of course, challenges remain. No large-scale, labeled SAR dataset exists for supervised training. Manually labeling pixel-level motion across thousands of images is nearly impossible. Future work must focus on domain adaptation, training models on synthetic SAR data, incorporating physical constraints like conservation of mass, or fusing SAR with optical or altimetry data. Long-term sequences could enable seasonal-scale monitoring, tracking how ice motion evolves over months, not just days. And perhaps most excitingly, this opens the door to real-time, AI-powered ice drift estimation. Imagine a dashboard that updates every few hours, showing not just where the ice is, but where it's going, with full spatial coverage. This study proves that pre-trained deep learning optical flow models are not just feasible, but operationally meaningful for sea ice drift estimation. They deliver sub-kilometer accuracy. They capture coherent regional patterns. They're robust, scalable, and transferable. Yes, the raw numbers may look modest compared to benchmarks like KITTI or Sintel. But in the Arctic, where motion happens over tens of kilometers, a few hundred meters of error is a rounding error. The real breakthrough isn't just the precision, it's the paradigm shift. From sparse, point-based measurements to dense, continuous pixel-level motion fields. We're no longer just watching the ice move. We're seeing it think with the eyes of a neural network. And that changes everything.